Considering whether to attend a 2-day seminar on the 2005 National Electrical Code or enroll in an IVY Tech course, here's a breakdown to help you decide. A seminar is typically a shorter program, lasting around 2 days. It often focuses on specific topics, such as updates to the 2005 National Electrical Code. Seminars provide a quick overview and update on code changes. An IVY Tech course is a more comprehensive program. It covers a wider range of topics within the National Electrical Code. Completing an IVY Tech course requires more time and effort. If you need a quick update on the 2005 National Electrical Code and possess limited experience with the code itself, the seminar might be a suitable choice. Conversely, if you are seeking a more thorough understanding of the code, the IVY Tech course would be a more beneficial option. The difficulty level of the seminar will vary based on your existing knowledge and experience with the National Electrical Code. If you're relatively new to the NEC, you might find it challenging to keep up with the material. However, if you have some prior experience and have engaged in self-study, you should be able to follow the seminar's content with focused effort. Most seminars are designed to offer an introduction to the topic and are generally not intended to be overly technical in nature. Continuing education units, or CEUs, are widely recognized across various organizations and industries as a means of demonstrating continuous professional development and education. Even if your current employer does not directly acknowledge American Traco CEU, they can still serve other valuable purposes. Firstly, they can be used for maintaining professional licenses or certifications. Secondly, they can aid in qualifying for membership in professional organizations. Thirdly, they can contribute to career advancement by showcasing your commitment to ongoing education. Deciding whether the seminar is worthwhile ultimately depends on your individual needs and objectives. If your primary goal is to obtain a rapid overview of the 2005 National Electrical Code, the seminar could be a good fit. However, if you are aiming for a more in-depth and comprehensive grasp of the code, the IVY Tech course would be the more appropriate selection. The perceived difficulty of the seminar will be influenced by your previous experience with the National Electrical Code, but with dedicated effort, you should be able to keep pace. Furthermore, the CEU earned from the seminar may offer advantages such as assisting in the maintenance of licenses or facilitating qualification for professional organizations. Both paths offer distinct advantages depending on your goals and existing knowledge. Consider what you hope to achieve and choose the option that best aligns with your professional development aspirations. Also, when looking at the NEC, understanding how to apply its tables, such as 310.15b16, is critical for determining conductor ampacity. This table provides ampacity values for insulated conductors rated up to 2000 volts based on their insulation type and installation conditions. For example, a copper conductor with THHN insulation in a 30 amp circuit might require a 12 American wire gauge conductor, assuming the ambient temperature and number of conductors are within the table's parameters. If the ambient temperature exceeds the table's reference temperature, correction factors must be applied to reduce the allowable ampacity. These correction factors are found in tables like 310.15b2. Similarly, if multiple current-carrying conductors are bundled together, adjustment factors from tables like 310.15 cone must be applied. These adjustments account for the increased heat generated by closely spaced conductors. For example, if you have 7 to 9 current-carrying conductors in a raceway, the ampacity must be reduced to 70% of the table value. Overcurrent protection is another critical aspect covered in the NEC. Article 240 addresses overcurrent protection devices such as circuit breakers and fuses, which are designed to protect conductors and equipment from overloads and short circuits. The standard overcurrent protection rule is that the overcurrent device should be sized to protect the conductor's ampacity. For example, a 20 amp circuit typically uses a 12 American wire gauge conductor with a 20 amp circuit breaker. However, there are exceptions to this rule, such as this found in 240.4b, which allows the NEC standard overcurrent device size to be used if the conductor ampacity does not correspond to a standard overcurrent device size. Grounding and bonding are essential for electrical safety, and the NEC provides detailed requirements in Article 250. Grounding ensures that non-current carrying metal parts of an electrical system are connected to the earth, providing a lower impedance path for fault current to return to the source. Bonding connects these metal parts together to create an electrically conductive path, minimizing voltage differences and reducing the risk of electric shock. Key concepts include the grounding electrode system, which consists of electrodes like ground rods, ground rings, or metal water pipes. The grounding electrode conductor connects the system's grounded conductor to the grounding electrode. Equipment grounding conductors provide a path for fault current to return to the source, ensuring that overcurrent devices trip quickly to clear the fault. Understanding these fundamental aspects of the National Electrical Code, including ampacity calculations, overcurrent protection, and grounding and bonding, is crucial for ensuring electrical safety and compliance in any electrical installation. Proper application of these principles helps prevent electrical hazards and ensures the reliable operation of electrical systems. Remember that specific requirements may vary depending on local codes and regulations, so always consult the latest edition of the National Electrical Code and local amendments for the most accurate and up-to-date information. In addition to the core concepts of ampacity, overcurrent protection, and grounding, the National Electrical Code also covers a wide range of other important topics, including wiring methods, equipment installation, and special occupancies. Wiring methods refer to the different types of cables, conduits, and raceways used to install electrical conductors. The NEC specifies the permitted wiring methods for various applications, taking into account factors such as environmental conditions, voltage levels, and fire resistance requirements. Common wiring methods include non-metallic sheathed cable, often referred to as Romex, which is commonly used in residential wiring. Electrical metallic tubing, or IMT, is a thin-walled conduit often used in commercial and industrial applications. Rigid metal conduit, or RMC, is a thick-walled conduit used in areas where greater physical protection is needed. Each wiring method has its own set of installation requirements, including support spacing, bending radii, and termination methods. Proper installation of wiring methods is essential for ensuring the safety and reliability of the electrical system. Equipment installation covers a wide range of electrical equipment, including panel boards, transformers, motors, and lighting fixtures. The NEC provides detailed requirements for the installation of each type of equipment, addressing issues such as clearances, ventilation, and overcurrent protection. For example, panel boards must be installed in readily accessible locations and must have sufficient working space around them to allow for safe maintenance and repairs. Transformers must be protected from overloads and short circuits, and they must be properly ventilated to prevent overheating. Motors must be installed with appropriate disconnecting means and overcurrent protection, and they must be grounded to prevent electric shock hazards. Lighting fixtures must be installed in accordance with their listing and labeling, and they must be supported independently of the suspended ceiling grid. Special occupancies refer to locations that have unique electrical requirements due to their specific characteristics or uses. The NEC includes specific requirements for a variety of special occupancies, including hazardous locations, healthcare facilities, and swimming pools. Hazardous locations are areas where flammable gases, vapors, or dust may be present, creating a risk of explosion or fire. The NEC classifies hazardous locations into different classes and divisions based on the type and likelihood of the hazard. Electrical equipment installed in hazardous locations must be specifically designed and listed for use in those environments, and it must be installed in accordance with the NEC requirements for hazardous locations. Healthcare facilities have unique electrical requirements due to the critical nature of the services they provide. The NEC includes specific requirements for essential electrical systems, which are designed to provide backup power to critical areas of the facility in the event of a power outage. These systems must be tested and maintained regularly to ensure their reliability. Swimming pools also have unique electrical requirements to protect swimmers from electric shock hazards. The NEC includes specific requirements for bonding of metal parts, grounding of electrical equipment, and the installation of ground fault circuit interrupters, or GFCIs, to prevent electric shock incidents. Understanding the NEC requirements for wiring methods, equipment installation, and special occupancies is crucial for ensuring electrical safety and compliance in a wide range of applications. Always consult the latest edition of the National Electrical Code and local amendments for the most accurate and up-to-date information. Furthermore, let's consider some practical examples of how the National Electrical Code's requirements are applied in real-world scenarios. Suppose you are wiring a residential kitchen. According to 210.52b, at least two 20A small appliance branch circuits are required to serve the countertop receptacles. These circuits must not serve any other outlets. The receptacles must be spaced so that no point along the countertop is more than 24 inches from a receptacle. Additionally, all receptacles within 6 feet of the kitchen sink must be protected by a ground fault circuit interrupter, or GFCI, as per 210.86. This ensures that if a fault occurs, the GFCI will quickly trip the circuit, preventing electric shock. In a commercial office building, the electrical system must be designed to handle the demands of computers, lighting, and HVAC equipment. According to 220.14k, a load of not less than 3.5 volt amperes per square foot must be included for general lighting and receptacles. The NEC also requires that branch circuits supplying data processing equipment have an ampacity not less than 125% of the connected load, as per 645.5a. This ensures that the circuits can handle the inrush current when the equipment is turned on. Additionally, the NEC requires that all metal raceways and enclosures be bonded together to create a low impedance path for fault current, as per 250.96. This helps to minimize voltage differences and reduce the risk of electric shock. In an industrial facility, the electrical system must be designed to handle the heavy loads of motors, machinery, and other industrial equipment. Motors must be protected from overloads and short circuits, and the NEC provides detailed requirements for motor protection in Article 430. For example, a motor with a full load current of 20 amperes must have overload protection sized at not more than 125% of the full load current, as per 430.32a. This ensures that the motor will be protected from overheating due to overloads. Additionally, the NEC requires that all metal parts of the motor and its associated equipment be grounded to provide a path for fault current, as per 430.121. This helps to prevent electric shock hazards. When working in a hazardous location, such as a chemical plant or a grain elevator, the electrical system must be designed to prevent explosions or fires. The NEC classifies hazardous locations into different classes and divisions based on the type and likelihood of the hazard. Electrical equipment installed in hazardous locations must be specifically designed and listed for use in those environments. For example, equipment installed in a Class I Division 1 location must be explosion-proof, meaning that it is designed to contain any explosion that may occur within the enclosure. Additionally, the NEC requires that all wiring in hazardous locations be installed in rigid metal conduit or other approved raceway, and that all connections be made with explosion-proof fittings. These practical examples illustrate how the National Electrical Code's requirements are applied in a variety of real-world scenarios. By following these requirements, electricians and electrical engineers can ensure the safety and reliability of electrical systems in residential, commercial, and industrial settings. Remember to always consult the latest edition of the National Electrical Code and local amendments for the most accurate and up-to-date information. Now, let's discuss some of the key changes and updates that have been incorporated into recent editions of the National Electrical Code. Keeping abreast of these changes is crucial for electrical professionals to ensure compliance and maintain the highest standards of safety. One significant area of change in recent editions of the NEC relates to arc fault circuit interrupters, or SCIs. SCIs are designed to detect arc faults, which are dangerous electrical conditions that can lead to fires. The NEC has expanded the requirements for fire protection in dwelling units to include more areas, such as bedrooms, living rooms, and hallways. This increased fire protection helps to prevent electrical fires and protect occupants from harm. Another area of change relates to ground fault circuit interrupters, or GFCIs. GFCIs are designed to protect people from electric shock by detecting ground faults, which occur when electricity flows through an unintended path to ground. The NEC has expanded the requirements for GFCI protection to include more locations, such as outdoor receptacles, bathrooms, and kitchens. This increased GFCI protection helps to prevent electric shock injuries. Recent editions of the NEC have also included changes related to surge protection. Surge protective devices, or SPD, are designed to protect electrical equipment from voltage surges, which can damage sensitive electronics. The NEC has added requirements for SPD in certain applications, such as dwelling units and critical care areas of healthcare facilities. This helps to protect valuable equipment from damage due to voltage surges. The NEC has also incorporated changes related to energy efficiency. The code now includes requirements for energy-efficient lighting, HVAC systems, and other electrical equipment. These requirements help to reduce energy consumption and lower utility bills. In addition to these specific changes, the NEC is constantly being updated to reflect new technologies and best practices. The NEC is revised and updated every 3 years, and it is important for electrical professionals to stay informed about the latest changes. One way to stay informed is to attend training courses and seminars on the NEC. These courses can provide valuable insights into the latest changes and help you understand how to apply them in your work. Another way to stay informed is to subscribe to industry publications and online resources that cover the NEC. These resources can provide timely updates on code changes and help you stay ahead of the curve. By staying informed about the latest changes to the NEC, you can ensure that you are providing the safest and most up-to-date electrical services to your clients. Remember to always consult the latest edition of the National Electrical Code and local amendments for the most accurate and up-to-date information.